guess I'm late. I think I'm late. Sorry about that. Sorry about that. Sorry about that. I'm just opening the live thing to see what's happening. I sort of got carried away. uh, Hello. Hi. I'm around. Yeah, I got a little carried away when I was like sort of preparing for this discussion session, and I didn't realize what the time was actually, and I'm sorry. I'm here late. I'm 3 minutes late, and we'll look at it though. So, hi everyone. My name is Zach, and I'm an open source software developer, and I'm using the advent of code December 2025 to kind of discover Verilog very detailed. I'm somewhat familiar with Verilog and digital design. I mean, I did cover quite a bit of digital design. I think I've done a semester on this in uni, although it's been more than 10 years, maybe 15 years, more than 15 years that since I was in uni. So I've forgotten most of this part, most of this stuff, and most of my time has been spent as a software engineer. So I've been writing software rather than designing hardware. So understandably, things are not as straightforward as they used to be. So anyways, I happen to have run into a really awesome course, hands-on FPGA. Hands-on FPGA done by the wonderful Venkat Rangan, who also happens to own Tinyvision.ai. I'm just going to show you this. This is just a preamble before the thing. Who happens to own Tinyvision.ai, and he does a lot of stuff. He has FPGA products. And anyway, so this is I think this is an 8-week module. I think it's a semester of trying to get really very grippy with FPGAs and trying to use them and see what can happen in them. And so what I'm going to do today is I'm going to go through the week two, and I'm going to go through the material, and then I'm going to spend maybe tomorrow and the day after and to try and do a couple of the challenges, maybe even do all the challenges. We'll see. They're quite simple. I have done most of them, but we can. It never hurts to kind of walk through these things and build through them quite nicely. So I'm going to spend a bit of time doing this. What I'm going to do today is kind of walk through the presentations over here. The links to the presentations are on the week two markdown document. And what I'm going to do is basically, just a moment, please allow me to pause. Thanks for waiting. I got a smoothie from my wife. Yeah, it's amazing. It's amazing the life I live. Okay, cool. So let's go on. Let's get on with this. The main point of this thing is to kind of like try and observe the real basics of this thing and understand what really happens in FPGAs. And that way we can build really robust, really powerful designs, and we can also debug existing designs. It's way less about being capable of building new designs at the moment for me, and it's more about being able to wade into existing designs and to be able to use them, to be able to debug them, and to be able to understand them, and to be able to put software in them on top of them. So a lot of the times you develop hardware with FPGAs. You make custom hardware, and what you want to do is you want to put some modules of software on top of this hardware, and you want to use it in some sort of weird way or something of the sort. And also you design like fast things and so on and so forth. So the main reason I'm doing with this, I'm doing this sort of low level or very basics or very fundamental cover-ups of FPGAs is because I'd like to understand them at a very intuitive level. Well, yeah. So and as it follows, in order to do that, it really helps to understand the minutiae of stuff, to just like go down to a level where you can understand what is happening symbol by symbol. And in code, we usually say you try and understand every line, line by line. You understand each line, you understand each token, and you see what it's doing, you know what it's doing. And once you can do that in code, it becomes quite simple to just carry into things and to be able to understand things. And that is why the nature of this sort of advent of FPGA for me is going to be doing about fundamentals, because once I feel as though once I really understand the fundamentals, it becomes really easy to build up later and to do things that are more complex. So just today we're going to walk through the material, and then later throughout the rest of the week, we're going to be doing the tasks and the challenges. They're quite simple. It's doing binary representation, binary algebra, combinational logic, and a bit of logic design. It's genuinely, I think, very simple, but it like I said, learning all these little things is going to compound into big things. And the quicker you cover the little things, the quicker you get to the big things, and suddenly we'll be able to be debugging big CPUs and small CPUs and such. A funny thing is, I did actually do a RISC-V CPU. I did do a RISC-V CPU, and I got my CPU works. It's on one of the boards. It's on one of the Arduinos and UPduinos, but it has a problem, and it has a problem in simulation, but it doesn't have to say it. It doesn't seem to have the same problem in actual running. So I've done a little bit of complicated stuff. I understand a little bit of complicated stuff, but I really would like to be able to go back to the beginning and kind of understand this really, really well, and in that way do more stuff. Anyways, that's the general information out of the way. That was a long 7 minutes. If anyone has any questions before we start going through this slide deck, and the slide deck is on the hands-on FPGA course, and it's the second slide deck from Professor Chuck Paterus. The first one is just an explanation of what is happening. It's really very simple. It's just an overview of what we'll cover today, basically. It's already in this. So does anyone have any questions? I see a couple of people online. Does anyone have any questions before we go on? Amazing. No questions so far. That's okay. I'm either doing something really complicated, or I'm doing something really simple that everyone already understands. Or I'm doing it in a way that no one understands. So please tell me if I'm just bumbling about and you don't understand what I'm doing. I appreciate such feedback as well. Okay, cool. So anyways, I think the spirit of this is that the thing we're going to learn is not about the thing, but it's about how to think about the thing, really. The function of education is to teach one to think intensively and to think critically. Intelligence plus character, that is the goal of true education, by Martin Luther King. So today's thing, what we're going to do today is we're going to go through, I'm going to skip all of this are introductions. Okay, cool. So this is kind of the layer of computing that we're looking at. So there's software at the top. There's all those software, Java, Python, C++, C, all of those things. There's software at the top, and then there's a compiler below that, and then there's an operating system below the that is things like it could be a real-time operating system, it could be an event-driven operating system, it could be a general operating system, whatever sort of operating system. That's what your software really runs on sometimes. And then if you happen to be an embedded developer and you write firmware, your firmware will likely run on the hardware itself through the instruction set and such. And those are things like ARM, the ARM instruction set, the RISC-V instruction set, which by the way is very, very, did you know RISC-V instruction set? The RISC-V instruction set is just 5 pages long. It is just 5 pages long, PDF. I have it on my other computer, but it is insanely brief. It is insanely brief. I think this could be the one. I don't know if this is the one. No, this is not the one. Oh, man, I wish I knew where to find it. But really, it's is it a cheat sheet? Let's see if it's a cheat sheet. Am I looking for the cheat sheet or something? But I'll find it on one of my other streams actually documents this, but it's extremely short. It's 5 pages long, maybe, and you should be able to like cover the whole of the instruction set and understand it, and basically from it you can do some pretty cool implementations. So that is the instruction set architecture, and then below that is the microarchitecture and the register transfer level stuff, which is what this Advent of Code series is going to be aimed at, of which this is day 3. I missed day 2 because I thought about things too much and then I didn't do them, so I need to just stop overthinking stuff and kind of do my stuff. Yeah, so I missed days 2, but all's good, all is good, all is well. So the thing that we're going to cover today is the hardware that is below the instruction architecture. This is things like the microcontroller. This is things like if you make a system on a chip, basically. It's basically the stuff that ends up being on a system on a chip or of some sort. So we'll as we go along, these terms that I'm speaking will become very familiar. They're quite familiar with me because I work with them quite a lot, although I'm working on the software side and I'm trying to learn how to debug and test the hardware side. And it's weird because hardware in FPGAs is actually code you write that becomes hardware. So it's not an actual piece of hardware, it's some configurable logic inside a FPGA which becomes hardware. Anyways, I'm assuming that you're watching this, you know about FPGAs and all of that stuff. So, and the first foray into this is to sort of understand numbers or counting and number systems. So there's, I think, 3 number systems. There's a lot of number systems. That was a mistake of me. There's a lot of number systems. Some of the popular ones are like octal, and then there's hexadecimal, and then there's decimal, and then there's binary, and there's more than that, and a lot of them have existed. But when we're using binary numbers, which have only 2 digits, binary numbers have only 2 digits. They have an on and an off, a 1 and a 0. And using binary numbers, we can represent decimal numbers, we can represent negative numbers, we can represent letters and characters, and we can represent anything that you can count, anything that you can enumerate. We can represent using binary numbers. And as Chuck says here, you don't really necessarily need ones and zeros. You could represent them with some sort of. He uses rocks. You could use sheep. You could use sticks. You could use something that is there and something that is not there, which is sort of like a build up to somewhere we will end up later, which is Boolean logic. And Boolean logic is the fact of it being the 2 states existing, an on and an off existing, and a 1 and a 0 existing and such. Okay, cool. So let's look at how far you can count with some arbitrary sort of thing. So with one box that you can fit n things, you can count n things. So in this point, if you can fit 18 rocks in a box, you can count up to 18. with two boxes, each fitting half of those 18 rocks, so which is, so let's say 9 rocks each, you can count up to 99, because you can count up to 9 on one, and then you can have a tens column which can count up to you can count which can also have we can count, sorry, I'm confusing myself. So you can have these columns. You can have a zeros column and a ones column and a tens column and a hundreds column and a thousands column and a million. This is why a million has that many zeros after it, and a 10 only has 1 0 after it, and 100 has two zeros after it. The 2 zeros after it indicate how many times you've flipped over, how many digits you've used, so that you've flipped over enough to get to the 1 at that point. And then once you get to the 1, you count from a 10, you go to an 11, and you go to 10s, and then you go to 20s, and then you go to 30s, and then you go to 40s, and then you go to 50s, and then you go to 60s, and then you go to 70s, 80s, 90s. Once you get to 100s, the second digit becomes a 0, and then you get a hundreds column, and so on and so forth. So hypothetically, if you had something with n boxes, you would be able to fill it with 2 to the power of n minus 1. So for 18, 2 to the power of 18 is 262,144. But we can fit in 2 to the power of n minus 1. So for say, let's say 2 of them. Let's say we had two boxes. How many can you fit in? You can fit in 0 0, and then you can fit in 1 0, and then you can fit in 0 1, and you can fit 1 1, and those are 4. So 2 to the power of 2 minus 2 to the power of 2 minus 1, which becomes 3, and if you start counting at 0, 3 is actually 4. Because there's a 0, there's a 1, there's a 2, and a 3, so it's 4. Okay, and this is, if you're watching this, you know computers, and if you ran into that title, you basically understand that counting starts from 0. Okay, cool. So the next thing, this is kind of explaining how those zeros occur. You add a digit, you increment a digit, and then once you increment that digit all through the digits that you have, so say you have, like in this one, you have 0 to 9. If you increment a digit from 0 all the way to 9, once you get to 9, you're going to roll over. So you're going to move it to 1 to the left, and then you're going to start again, and then you're going to start from 0, and then all the way to 9 again. Once you get to 9 again, you roll over, and you do something to the, you add 1 to the left, so the 1 on the left becomes a 2, and then you keep going, and you keep going, and you keep going all the way until you get to 999,999, whatever. Okay, so that's the maximum number you can represent with 4 decimal digits, which is 99999. 4 nines, 9,999. And you can do this. You can do this with decimals. You can do this with hexadecimals. You can do this with octals. You can do this with binary. You can do this with as many. And so whenever you hear, that is why higher bit precisions are usually that much more. So it's usually better to have something that has a 12-bit precision more than something that has a 5-bit precision more than something that has a 6-bit precision. And a 16-bit precision is, when you see ADCs and DACs, ADC precision, ADC precision, it's usually said in bits. So you can see ADI precision ADCs from 8-bit to 32-bit resolution. So they mean that you can, the maximum number and the minimum number are between those ranges, and with a higher range, you have more of a smaller division to make. This is sort of something in a Gaussian scale. The Gaussian scale is, well, it's all stuff I don't know. So the Gaussian scale, or the Gaussian function, is a real thing where the it's how you go from 0 to 1. And if you actually travel from 0 to 1 through all the decimals, 0.0000001, and then you increment that and increment that, this is real numbers or something. So the values are too many to be able to be quantified, basically. So the more bits you have, the more you can subdivide the things that you're representing, which means the more accurate and the more precise you can be. I don't know about accuracy, because accuracy and precision are different things. But if you read DSP for engineers, DSP for engineers, accuracy versus precision. Precision. Let me see if I can find it. Precision and accuracy. So they're two different things. And if you can read this, if you can get to this, you can find out what I'm talking about and whatever. Cool. So let's keep going here. I wanna do this quickly. So binary numbers, such as they're made up of zeros and ones. I think this is 52, and we can do so 0th, or rather the zeros number is or the ones. Is it the zeros or the ones? I think this is the zeros. So you can multiply this by 2 to the power of 0, and then you can go 0 times the value times 2 to the power of the position, so 2 to the power of 1, and then you can add all of them. 1 times 2 to the power of 2, 0 times 2 to the power of 3, 1 times 2 to the power of 4, and then 1 times 2, and then you can add all of them. If you add all of those, this number ends up being 52. So there is no 2, 3, 4, 5, 6, 7, or 8 in binary. There is just a 0, then a 1, and then you roll back. You add 1 to the left, and then you roll back, and then you add 1 to the left, and you roll back, and so on and so forth in binary numbers. I'm rushing through this because it's mostly introductory stuff, and I don't see anyone having any questions. So if I had questions, I would stop, but this is mostly introductory stuff. When we start actually doing code and doing Verilog stuff, it's going to be quite fun, and that's maybe tomorrow or the day after. So but this is just customary that we have to go through this. Okay, cool. So binary numbers themselves. This is a comparison of binary numbers, decimal, binary, octal, and hexadecimal numbers. So 15 in decimal is F in it is 1111 in binary, and sorry, I read that as F, by the way. So it's 1111 in binary. It's 017 in octal, because octal is 0 to 7. Okay, binary is 0 and 1. Decimal is 0 to 9. Hexadecimal is 0 all the way to F. Okay, so digits are 0 all the way to F. So there's 0 all the way to 9, and then you go A to F, and then F is number 15, basically. So number 15 in binary is 1111. In octal is 017. In decimal, it's 01111, which is 0F, 0 cross F, basically, in hexadecimal. This is a comparison of the number systems, and these are number systems. Octal is a number system, hexadecimal is a number system, and binary is a number system. And these are all, they all have their advantages, and they're made for a reason or for not a reason, basically. That's the thing you can just look at them for, basically. Okay, so this is cool. And then whenever you need to do negative stuff, negation and stuff, you need to divide by a negative, or subtract from a negative, or multiply by a negative. There's a concept that is called 2's complement. And the 2's complement says that on the most significant bit, if that is true, if the most significant bit is a 1, it is assigned a negative. And if it's not a 1, then it's assigned whatever, it's assigned, it's not a negative. And that way we can differentiate how do I say this? We can differentiate negative numbers and positive numbers, which also gives us a way of doing arithmetic between negative and positive numbers using the same sort of function, rather than having a specialized function for negative numbers and a specialized function for positive numbers. So 2's complements is a way of representing negative numbers in binary that enables us to do arithmetic and logic with or rather multiplication and division and all of those using the same functions that we would use for normal functions, basically. I'm droning on quite a bit. Does anyone have any questions at this point? I'm droning on quite a bit. Okay, cool. So we can keep going. So if you use hexadecimal, you can present which also you can call them 8-bit binary numbers. 8-bit, if you have 8 bits of binary, which is actually a byte, isn't it? Bits in a byte. It might be a word. I keep forgetting these things. It's not very intuitive to me. 8 bits, yes, but it could also change depending on the system that you're on, because a bit could be well, those are words. Words are the ones that change by system, I think. But anyways, 8 bits is a byte. And if you have a byte, you can represent text characters, because if you there's a it's called ASCII. American what is ASCII? What is ASCII? ASCII. This is high school stuff. American Standard Code for Information Interchange is a character encoding standard for representing a particular set of 95 English language focused printable and 33 control characters, a total of 128 code points. And then what is Unicode? It's going to be a complete it's going to be a competing standard of the same sort, basically. Unicode, also known as the Unicode standard, is a character encoding standard maintained by the Unicode Consortium, designed to support the use of text in all of the world's writing systems that can be digitized. So one of them is supremely English focused, and the other one is sort of like anything that can be written in the world can be represented in this sort of coding system. So, and I think this is does Unicode start where ASCII ends? Key factor size. It's obvious. 154 written skips and dimension emoji 2. So key factor number 2. Unicode is equal to ASCII is equal to as I expected. That's a really good line. That's a really good line for me. So for backwards compatibility, the first 128 Unicode characters point to ASCII characters. So yes, they are sort of Unicode starts, or Unicode is an extension of ASCII. So that's cool. So this is both Unicode and ASCII. What we're looking at is Unicode and ASCII. So using these 8-bit binary numbers, we can represent this many characters, which is sort of what we can write. And if you can think about this, and you think about what sort of material we've covered so far in the last half hour, you can realize that using electrical signals, or rather using signals in FPGAs, you can write whatever message you want. You can write whatever message you want, and you can also receive whatever message you want, which is quite exciting, because now you can start seeing how electrical signals become some sort of data that you can use, or that you can carry along, or that you can send it down the wire and come back with it, and sort of the same thing. Okay, cool. So let's look at the next thing. Unsigned hex numbers as 4-bit signals. So count is an example of a 4-bit signal. It corresponds to 4 separate wires. This is the thing that we were speaking about just now. four physical wires in a circuit. So if you have a circuit, if you have a breadboard and you have like a battery on one end and you have a physical wire, and you can connect this battery to this wire to ground or to the VCC terminal or whatever, the voltage terminal. Basically, with four wires, you can end up representing all of the hex numbers. You can represent 0, you can represent 1, you can represent 2, all the way to F or 15. So, and you would start with the sort of like the least significant byte all the way to the most significant least significant bit, LSB, and the highest significant bit, or most significant bit. And that's how you would kind of, so 0 is going to be that one, and 3 is going to be the highest one, and then you can, using that, you can basically chart out this numbers. And here we can see here, hex 0 is that 000, which is also decimal 0, 1 is 001, and 2 is 0010, and 3 is 11 at the end, and 4 is going to be 100, and 5 is going to be 101, 6 is going to be 0110, and 7 is going to be 0111. I always used to confuse 7 and 3. 8 is going to be 100. 8 always looks like 1,000 to me, and 9 is going to be 1001, and so on and so forth, all the way to 15, or F, which is 1111. So we can basically use power signals from a battery and 4 wires, and using 4 wires and power signals and fast enough switching mechanism, we can send a message, because I can send you all of this character encodings and whatever. And if you think about it, if we had 8 wires, I could send you full text messages. Basically, I could send you full text messages. If you're on the other side of this wires on the other end, I could plug them in. It might be slow, it might be cumbersome, there might be a lot of mistakes. We might have to come up with a control some control messages on top of that would enable me to tell you that, hey, wait, you're going to have to wait, or this is a backspace or something of the sort, and we can send you messages, and we can send them between each other just fine. Okay, most of this was invented. Boolean logic comes from George Boole, a mathematician from, I think, the is it 1800s? I think it was the 1800s or something. So the 17th century. 17th century? 19th? 18th century or whatever. And he was basically the inventor of Boolean logic, and it comes from his name, although it grew into popularity or into quite a lot of use after his life. And he died with pneumonia and with some like very mystical stuff in the way he was treated and stuff. But then at some point we moved from Boolean logic to Principia Mathematica, and it almost seemed like Boolean logic was going to be this like phase in history that was going to be forgotten. But then somewhere in the 40s or in 1949 was Claude Shannon, who was an American mathematician, and he invented something called a digital circuit. And a digital circuit used digital signals to send messages from one side to the other, and all of these things. And basically, here we are, streaming video over computers, about computers, on how computers work. We're streaming video on a digital circuit, about digital circuit, and the video is on the history of digital circuits and how to do better and faster digital circuits. Did I say digital circuits enough? I'm having too much fun. Okay, cool. So let's keep going. So remember the thing about us having 4 wires and me being able to send you 15 characters. What happens when I want to send you more characters? What happens when I want to send you complex messages? Then we start ending up in this place where we need to have this sort of control layer on top, where I can you know, I can combine things, I can send things and all of this and such. Basically, what happens when we want to automate this digital circuit, so that rather than me plugging stuff in, there's rules of how two things or three things or four groups of things can be combined into stuff. And that's where we learn into something called logical gate or logic gate. And logic gates are devices that perform logic operations on one or more inputs. Let's look at logic gates. Logic gates. So, yeah, logic gate. A logic gate is a device that performs Boolean logic, a Boolean function, uh, a logical operation performed on one or more binary inputs that produces a single binary output. This is almost like, this sounds quite a lot like a neuron, you know, because a neuron is the same thing. You give it binary outputs and it has a binary output. You give it binary inputs and it has a binary output of some sort. So you can see here. So a logic circuit diagram for a 4-bit carry look ahead binary adder. And there you go. We probably will end up making one of this and having to walk through it so that we can understand it, because the assignment for this thing that we're doing right now is to make an adder. So maybe, I don't know if it's an adder or it's a complete adder or a full adder or a half adder, but I know we have to make an adder at some point in the week 2 of this thing. But for right now, what we're doing is, this is something I learned from Ben Cook, I think. Ben Cook maybe. Ben Cook. Ben Cook. How to learn, isn't it? Isn't it? Cramming. The video on cramming. I don't. How to cram so it works. Oh my word. How to ace college. This is not high school. Anyways, I'll find the link. I need to just go like to my subscriptions or something and just find out which one it is. But basically, uh, the concept, his concept is that, on cramming, is that if you spend a lot of time in the beginning and cram as much as you can, that way whenever you're going through the actual course material, whenever you're going through the exercise in the course, whenever you're learning something in the course, what happens is, whenever you encounter something, it's usually the second time you've encountered it, and you have a perception, you have a way, you already have a thing, you already have an orientation or a perspective of looking at the thing that you're encountering. So if you spend time in the beginning to cram about stuff that you're going to work on, then what happens is, when you actually get to a point where you're working on the thing, you already know, the term. This is the second time you're getting acquainted with it, so it becomes way easier to kind of encounter. I really wish I could. I really wish I could. I could present that. I do not want to see that. This is not what I wanted to do. Ben Cook. Let me see subscriptions. There's one. Let's see. yeah, this starts to show you who I am. I am a lot of people in a lot of different places. Um, Learn everything better? No. I'm trying to find out a thing. I'm trying to find out a thing. If you just joined, this is me trying to find out some source of information that I just shared, which is about cramming and why you need to cram stuff before you do them again. How to read a book effectively. Yes, that's the one. That's the one. No, no, someone. So many people make this videos. How do I not find the one I want? How to cram so it works. How did my video just degenerate into me searching on YouTube about stuff? Anyways, I'll find this, and the next time I do a stream, this is the first thing I'll share. But the essence is that what I am doing is that I'm going through the complete corpus of information. I'm trying to go through every bit of information that is available for this thing that I want to learn. And in doing so, I am putting it in my head and I am imprinting something. So that the next time, whenever I actually go to work on the thing itself, I already have a perspective and I already know the definition of the thing. So whenever I'm working on something, I have an idea of what I'm working on and what it was and everything, and then it becomes way easier for me to start actually doing actual stuff with it, that rather than just leaving, encountering it for the first time, getting confused and stopping. Basically, is basically what I'm saying. So logic gates are devices which perform logical operations on one or more input and produce a single output. So you can give it A, B, C, and if you give it A, B, C, and it'll depending on the values of A, B, and C, you'll get an output. And usually the way it works is if you have n inputs, then you have 2 to the power of n outputs. I mean 2n outputs, not 2 to the power of n outputs. 2n outputs. So here is a NOT gate, and a NOT gate says y is equals not x. So if you put in a 1, you'll get a 0, and if you put in a 0, you'll get a 1. Input 0, you get a 1, and if you put in a 1, you'll get a 0. That's a NOT gate. And you can combine them. There's a NOT gate, there's an AND gate, there's an OR gate, there's an XOR gate, exclusive OR, there's an exclusive NOR, and there's or an exclusive AND. I think there's a ZAND and all of those things. So here's a couple of gates and their input. So we have an input 1, an input 0, and an input 2. And depending on an input 0 and 1 and 2, input 1 and input 2, this is the result of the AND. So input 0 and input 1 0, input 2 0, AND becomes 0. So 0 and 0, nothing is true there. 0 and 1, 1 is true but the other one isn't. 1 and 0, okay, 1 and 1 is true, that is 1. So okay, and then you get an OR. If 0 or 0, you'll get a 0. If 0 or 1 is true, you get a 1. If 1 or 0 is true, you'll get a 1. If 1 or 1 is true, you'll get a 1. Okay, so that is an OR. And then you'll get a NOT AND. So NOT AND is going to be the negation of the ANDs. Okay, so you do an AND and then you do a negation of it, and as you can see here, it goes 1 1 1 0, and then AND is 0 0 0 1. And then there's a NOT OR, which is a negation of the OR, and then which goes like 0 1 1 1. You'll do an OR and then you'll negate it, and then you'll get a 1, and then for the rest you'll get a 0. Okay, cool. And then you have an exclusive OR. And an exclusive OR means it can, so 0 or exclusive or 0 is both 0. Okay, 0 exclusive OR 1, yes. 1 exclusive OR 0 is 1. 1 and 1 is going to not be this. In an OR, this would be 1, but in an exclusive OR, only one of them can be true, not both of them. So it's and then there's an exclusive NOR. So you will do an OR, and then you'll do a NOT on that OR, and then based on that not or, you will do an exclusive on that one, and that's it. So it's basically the negation of an XOR or an exclusive OR. Yeah, it's a negation of an exclusive OR because it's a 1. When an exclusive OR is 0, it's a 1. And so here's a couple of tables. There's a lot more types of gates that come with that, and we're almost there. So whenever you make circuits with gates, with logic gates, these circuits always depend on the current input rather than like software. When you're doing software, the current output will depend on the complete inputs that have preceded this. So some input will come in and it will set a certain state, and then another input will come in and it will set another state, and then you'll get an output. Whereas for combinational logic circuits, what really happens is I have this page somewhere, but I won't get distracted now. So for combinational logic circuits, what really happens is whatever the inputs are right now, they will determine what the outputs will be. So if one or more of the inputs changes, the outputs will also change. It's a zero memory. It's a memory-less system for combinational circuits. And this is a kind of a combinational circuit. Did we look at logic stuff? Did we look at logic gates or something of sort? I think there was a point where we looked at logic gates. Yeah. So this is a combinational circuit. This is what a combinational circuit is. If one of these inputs changes, then the output will change. Rather than in a software system, if one of the inputs changes and then there is some sort of state from all the other inputs, it might not actually change the output of the thing, and that's what is termed as a combinational circuit. And a combinational circuit, as described here, unlike sequential logic circuits, whose outputs are dependent both on their present inputs and their previous output state, giving them some form of memory, the outputs of combinational logic circuits are only determined by the logical function of their current input state, logic 0 or logic 1, at any given instant in time. And this seems like a little thing, but understanding this will make the things that are coming up become really simple. Understanding that this thing does not hold any memory and it doesn't remember backwards, and that everything is happening at the same time, it's a fully parallel thing. It's not sequential, it is parallel. So all the code is always run at all the time. Understanding this will make the learning curve for FPGAs and for digital design much simpler for one. I'm saying this to myself as anyways. Okay, cool. So functional description. A combinational circuit consists of logic gates, and these circuits operate with binary values, and the outputs of the combinational circuit depends on the combination of present inputs of present inputs. The following figure shows a block diagram of a combinational circuit. So you have a A, B, a C, and an N, and then you have an A, and not A, and not B, and a C, and an M. These are the results. Okay, cool. Design procedure of combinational circuit. Find the required number of input variables and outputs from a given specification. Formulate the truth table. If there are n input variables, then there will be 2n possible combinations. For each combination of input, find the input values. So earlier I misled you because I said there would be 2n possible outputs. It looks like what I meant is 2n possible combinations of the inputs. So if there's 60 inputs, there's going to be 120 ways of trying to combine them. Okay, and then once you have the ways of combining them, then for each of those you will determine what the output is, and then basically you've designed. Once you design a truth table for the thing that you're working on, you've made the circuit already. Now it just becomes a way of implementing it in code and such. Okay, cool. Finally, we get to FPGAs, because now we're looking at binary logic. We get to like something that actually represents the thing that we want to learn, the hands-on FPGA. So what are FPGAs? FPGAs are field programmable gate arrays, and there are arrays of gates, the things that we just talked about, nots, ands, ors, XORs, and I think if I'm not wrong, all possible logic can be implemented using not NAND gates. Okay, and NAND gates. It's either NAND gates or yeah. A NAND gate is known as a special type of gate, which is also known as a universal gate because it can be used to implement any other basic logic gates, logic gates, basically. That's what I'm saying. So what we really want to think about is how many lookup tables does an FPGA have? You see, because it's made up of all of these gates, so it has a number of lookup tables that you can use. These lookup tables are so important to the design of an FPGA that they usually form a part of the name. For example, what we are going to be using in this advent of code thing is going to be the Ultra Plus 5000 lookup table lattice ice40, which is the one that is, so it's the UP5K. And if you watch my last FPGA stream, you would know that this is actually one of them, because I was trying to use I was actually attempting to use the SB I2C, but then I didn't use it because as you can see. So it looks like that is it. That's what FPGAs are. Then FPGAs are not ASICs and they're not microcontrollers. FPGAs are more expensive than microcontrollers, but they're cheaper than ASICs. Well, they're cheaper than the first ASIC, not cheaper than all ASICs, because the first ASIC is gonna cost you like millions, and then after that, each ASIC could be like a dollar or even less. And ASICs are like basically hardware that is you design a circuit with FPGA and it works very well, and then you commit to having this circuit as the one that works. And so you instead of having a soft device that can be reprogrammed, you go and make a hardware device that just does that. It's a digital circuit that just does one function, and that's an ASIC. And a microcontroller, on the other hand, is something that is something with a sequential logic handler, which is something we call microcontroller CPU, and CPUs handle one instruction at a time, and that they're a little slower, they're limited, and once you get them in the configuration that they are, that's how you have to use them. You can't use them in a different way. Whereas with FPGAs, you can constantly change the hardware. Well, you can change the hardware by programming it in a different way. So you can make it this, and then you can change it to that, and then you can adjust it up and down and such. And if you have like weird requirements, let's say you have a system and it needs like 18 ADCs and 2 USBs or something, it's going to be very difficult to find a microcontroller that has those sort of stuff, peripherals. So FPGAs become very relevant here, and they're good at doing a lot of things in parallel and a lot of things really quickly. I feel like, and so I think the exercise for this thing is going to be writing a full adder. And here we have a full adder can add two 1-bit numbers A and B and carry C, and the full adder is a 3-input and 2-output combinational circuit. And this is the truth table for the full adder. And basically, if you can implement this, I think it's basically a case. This is, if you can use case statements in Verilog, and you can have this as evidenced, as you see. So AB 000, you can do that, and S and S and 0, and all of those values. Once you have the truth, like I was saying, once you've made the truth table for the problem that you're encountering, you already have the Verilog. You can use that, and you can go forward with that. The tasks that we're going to be doing. So tomorrow we'll work on a few tasks. They're going to be representation using binary numbers. Let's look at that. I think it's going to be some task on, okay, probably just reading that. Binary algebra, this is probably also just reading that. I won't read this. This is stuff that you can go through by yourself. Combinational SSI, this is combinational SSI components, so that's fine. What is SSI? Small scale integration combinational, i.e. logic gates, combinational gates. That's fine. And then logic design, this is the part that I would like to actually go. Yeah, we might go through this tomorrow. Kanagaf maps. Okay, cool. Kanaf maps. Okay, cool. So we might go through logic design tomorrow, and then the other thing that we will want to do is do some of the tasks. So I think in the hands-on FPGA, this one is going to be, no, not yet. The tasks here is to create, create a system Verilog design that combines what you learned today. You can do this online, although we will be using actual Verilog on an actual we'll be using actual Verilog on an actual on an actual FPGA, and we'll make an adder, and we'll make a test bench for that adder, and we'll do some bit width analysis, and we'll look at doing the advanced stuff, which is like doing negative numbers and twos complements, and read that. We might even cover all of this tomorrow, all of these challenges tomorrow, so that the next day we can actually go to week 3, which is getting started with logic design and Verilog simulations. Well, thank you so much for attending my lecture, and thank you so much for coming to this cramming session by me. And I'm going to try and keep on doing them. I'll try and not overthink stuff, and so that I can get to doing stuff. And I really appreciate your time and your attention. And remember to be daring, remember to fix things that exist, and remember to stand on the shoulders of giants. Thank you so much. Cheers. Bidding you bye till the next time I see you. Thank you. Cheers.